Hello dear students, welcome you all for Power System Operation and Control class. In the previous class, we have seen the automatic generation control. That is, we have studied it in second module as well as in the third module's first half. So the second half of the third module is now AGC in an interconnected power systems. Okay, so we have seen that AGC is used to keep down the frequency deviations, or the importance of having AGC in keep down the frequency deviations. When we have interconnected system, the AGC has to take into account the tie line flows. So we will study the load frequency control of interconnected system in this unit. We have seen in the case of an isolated system with which only the primary speed control, any change in system load will lead to steady state frequency deviation depending upon the droop or governor droop characteristics and the frequency dependence of the load. All the generation units equipped with governor control will have a change in their generation levels irrespective of where the load change takes place. To restore the frequency to the nominal value, we need to use a supplementary control which changes the load reference set point, which matches the prime mover power to variation the load. Okay, a group of generators coupled closely will swing together and make replaced by a single equivalent generator. The generator turbine also tend to have the same response characteristics. Such generators are said to be coherent, and the system is called control area. When the different control areas are connected, the objectives of the AGC should be: the first one, hold the system frequency close to the nominal value 50 Hz. Second one is to maintain a correct value of power interchange between control areas. And third one is the maintain the generation of each unit at the most economic value. So this is regarding the objectives of AGCs when it is connected in interconnected system. Okay, so directly we will move to the subject. So that is tie line control with primary speed control. So consider this figure 1 where two areas are connected. Here you can see area 1 and area 2 connected with the tie line which is having a reactance of X tie, or the power transfer from 1 to 2 you can take it as P12. Okay, the power flow from the 1 to 2 is taken as positive power flow, and the it is flowing from the area 1 to 2. So the power flow equation from the tie line area from 1 to 2 is given by, it's very simple, you can see here, P12 is given by E1 E2 divided by X12 into sine delta 1 minus delta 2, equation 1. See, in figure 2 it is electrical equivalent of the same system. See, first area is having one generator with its EMF E1 and angle delta 1, and its reactance is X1. Tie line reactance is X tie. Second area's generation is E2 and angle is delta 2. X2 is the reactance of the area 2. It is very clear in this figure, is it? Now, power transfer, we are knowing in power system analysis 1 you are seeing that one. P is equal to what? EV by X into sine delta, is it? It is what? E is the excitation voltage, V is the terminal voltage, X is the reactance. Same thing here with two generations here, A1 and 2. So P12 is given by E1 E2 divided by X12 sine delta 1 minus delta 2. So where X12 is given by X1 plus X tie plus X2, that is the reactance of the area 1, tie line reactance plus reactance of the second area. Togetherly we are calling it as X12. From the equation 1 can be linearized about the initial operating point. So we can make it as delta 1 as delta 10 and delta 2 as the delta 20. So the power transfer delta P12 it will change is given by E1 E2 by X12 cos of delta 10 minus delta 20 into delta 12. Okay, so the changes is what now here, delta is changed to delta 1 delta 2, and here delta 1 2 is used, where delta 1 2 is nothing but delta 1 minus delta 2. So T is equal to E1 E2 by x12 cos of delta 10 minus delta 20, which is given by P max cos of delta 10 minus delta 20. So it's very clear that E1 E2 by x12 is nothing but P max. Okay, and the T is called as the synchronizing torque coefficient. So if you put this one in equation 2, so delta P12 is equal to T into delta delta 1 minus delta delta 2. So this you can take it as equation 5. Now we'll see the block diagram. This is the two area system with the primary loop. The block diagram representation of the two area system with only primary control. A positive delta P12 means increase in power from 1 to 2, that is increase in the power flow from area 1 to 2. This is equivalent to the load increase in the area 1 or decreasing in the load area 2. Very simple, either it is an increase in area 1 or decrease in the area 2, or increase in area 1 and decrease in the load in area 2. Therefore the feedback from delta P12 has a negative sign for area 1 and positive sign for the area 2. Obviously, where a increase is taken place, there is a positive; where a decrease is taken place, there is a negative sign. Oh, sorry. In where the increase is, the feedback is given to area 1, where positive is taken place, feedback is negative for then, and where the decrease is taken place, no, there negative positive is the feedback. Okay, because feedback is the negative, so obviously it is reverse changes in sign. Okay, so we will now see how the system behaves for the change in the load. So this is a block diagram first with the two area system with the primary loop. You can see two areas is there. In between, these two are connected with the T, that is synchronizing torque coefficient is connected. Okay, so this is an important block diagram. You can see all these things, your simple models you are seeing in individual models. So now two models are now connected here. Now change of load in area 1. So considering the load change of delta PL1 in area 1, when the system is reached to steady state, both areas will have same steady state frequency deviation. So therefore delta omega is same as delta omega 1 equal to delta omega 2. That is the steady state frequency deviation. If we assume that mechanical powers are to be constant, the tie line and the rotating masses exhibit damped oscillation called synchronizing oscillations. For the area 1, we can write here delta Pm1 minus delta P12 minus delta PL1 is equal to delta omega D1. We can take this as equation 7. For area 2, we can write delta Pm1 plus delta P12, or you can write it as delta Pm2. Okay, delta Pm2 plus delta P12 is equal to delta omega D2. So we have further delta Pm1 is equal to minus delta omega by R1, and delta Pm2 is equal to minus delta omega by R2 with using the droop characteristics. Substituting this one in 7 and 8, we will get minus delta P12 minus delta PL1 is equal to delta omega into 1 by R1 plus D1, and delta P12 is equal to delta omega into 1 by R2 plus D2. Or by writing this one, delta omega is equal to minus delta PL1 divided by 1 over R1 plus 1 over R2 plus D1 plus D2. So this you can take the equation 11. And finally delta P12 is equal to delta omega into 1 by R2 plus D2, and substituting these things. So equation 7 to 12 are the new steady state condition after load change. The new tie line power flow does not require a knowledge of the stiffness constant as seen in the equation 12 just before. However, T is required to know how much phase angle difference will result across the tie line due to new line power flow. So we can write delta omega is equal to minus delta PL1 divided by 1 over R1 plus D1 plus 1 over R2 plus D2, which is nothing but minus delta PL1 divided by beta 1 plus beta 2, and delta PL2 is equal to minus delta PL1 into 1 over R by 2 plus D2 divided by 1 over R plus 1 plus D1 plus 1 over R by 2 R2 plus D2. So this can be written as minus delta PL1 beta 2 divided by beta 1 plus beta 2, where the beta 1 and beta 2 are the composite frequency response characteristics of the area 1 and 2 respectively. So this is regarding the change in the load in area 1, what happens. Okay, in the next class we will see what happens if in the change in area 2 and both the changes, one areas, both the areas, what are the changes are take place. For the time being, just now you can have a brief introduction on this one, and with the tie line control, how two areas are connected using a tie line, and electrical equivalent of this one, and different equations, and the two area system with the primary loops block diagram, and some the important equations regarding the change of load in area 1. Okay, if you find any difficulties you can ask me. So in the next class we will see how exactly the change in load area 2 and change in both areas will affect on this performance. Thank you.